All right, welcome back. This is the second homework video that I'm doing where we're going to go through problem 14. And this just presents us with the same scenario, just with two different forces. So we have a crate that is being pushed across the floor. We are told that it is moving at a constant speed, which is important. And we are told the magnitude of our force, which is 260 newtons. So we know that FA, which is this, is 260 newtons in both cases. Okay, we also know FG is 1200 newtons. We do not know what the constant speed is, but we do know that it is moving at a constant speed, and here's why that is important. If it is traveling with a constant speed, then its acceleration is 0. So what this tells us is the sum of forces is equal to 0 in both dimensions, which is super useful. So we need to write a free body diagram, right? We need to draw a free body diagram for both of these. So first we have in A where the crate is having the force applied this way. Now I'm going to move this arrow to here for reasons that will become clear later. So we have an applied force here. We have weight acting down. We have to have a normal force acting up. And we're talking about friction, so there has to be friction. I should be labeling these. This is the applied force, this is the weight, this is the normal force, and this is the force of friction. So our applied force is acting in two different dimensions. And you know what? I'm going to go ahead and move it back where it was, because that will be easier in the long run. So we have our applied force acting here. And we know that this angle is 20 degrees, because it tells us that the angle is 20 degrees below the horizontal. So that means this is 20 degrees, and if that is 20 degrees, then this is also 20 degrees. So we have in this component, we're going to have FAX, and then we're going to have an additional downward force of FAY. So let's do our triangle. Okay, we know this is 20 degrees. We need to determine the vertical and horizontal legs. We know that this is FA, and we know FA is 260. Excuse me. So in a rare turn of events, we can actually calculate the horizontal and vertical components. So we don't have to use equations. We can actually use these variables. So vertical is going to be opposite. Horizontal is going to be adjacent, as seems to almost always be the case. So the horizontal component, FAX, is equal to FA 260 times the x is adjacent, so cosine of known angle 20, and FAY will be the same, but sine. And we can actually get numbers for both of those. So 260 times the sine of 20 would give us 88.5 0.9. Jump the gun on my rounding. And then cosine would give us 244. And those are both going to be newtons. So once again, I need to switch to white because I'm running out of room. So I will switch to a white background and be back momentarily. All right, so in addition to getting the white background, I also moved this information up from the bottom because I realized looking at the video it was very, very difficult to see. All right, so now we're going to write our sum of forces equations. So I'm going to move up a little bit, and I'm going to redraw this, but without this initial arrow, like I did in problem 7. So we have our crate, we have weight down, we have normal force up, we have a resistive friction force to the left, and then we have the horizontal component of our applied force, FAX, and the vertical component of our applied force, FAY. And I almost forgot, this would be negative, as we can see here, which we actually don't need to report that yet, because it's a vector. Okay, so in our sum of forces equations is where we'll actually note the direction here. So we need to write a sum of forces for y and a sum of forces for x. Since x is simpler, I'm going to start with that one. So positive force is going to be FAX. So sum of forces in x will give us FAX minus the force of friction. And it is moving at a constant speed, which means A is 0, so this is equal to 0. And then we have our sum of forces in y, which would be the normal force, which is positive, minus the weight minus FAY. And this would also be equal to 0 because it is not moving up or down. Now, this gives us some useful information right off the bat. First off, we know that FAX is equal to the force of friction. So FAX is equal to the force of friction, which is equal to the normal force times the coefficient of friction. And then we can also get from this that the normal force is equal to the weight plus FAY. Yeah. All right, so I'm going to make a little bit more of a clearer delineation here. And we'll come to this side to finish this up. Now, let me look back real quick because I don't remember what we're actually looking for. So I'll be back in a moment. All right, we are calculating the coefficient of friction, which is what I was thinking, but I wanted to double check. Now, here's something that bears mentioning. Notice that the normal force is equal to the weight plus the vertical component of our applied force. So by pushing like this, we're actually increasing the work that we have to do because we're increasing the weight of the object that we're pushing on while we're moving. This is one reason why it's better to lift on something when you're going to push it rather than to push down on it. Because obviously if somebody's standing on a table, it's harder to move the table. Okay? So let's jump up here. I'm going to rewrite these two equations, and then we will see what we need to do. So I can drop this, so we have that. FAX is equal to the normal force times the coefficient of friction. And we have that the normal force is equal to FG plus FAY. So we can actually plug these in up here, and we get that FAX is equal to FG plus FAY times the coefficient of friction. So we can divide FAX by FG plus FAY, and that will give us our mu, which is what we're trying to find. So FAX was 244 divided by the weight of the crate, which was 1,200, plus the vertical component was 88.9. And that comes out to 244 divided by, 1,200 and 88.9 Yeah, okay. Doubting myself there for a second. That gives us 0.189 for our coefficient of friction, which is the first half of the problem. Okay, now that we have the coefficient of friction, part B tells us if the force is instead a pulling force at an angle 20 degrees above the horizontal, then what would the acceleration of the crate be? Assume the coefficient of friction is the same as it was in part A. So now, instead of our applied force being down, it's actually up. So we will have to write a new free body diagram, which means that we will need new sum of forces equations. But it tells us that the coefficient of friction is the same. And it tells us that this time we're accelerating. So we cannot set our sum of forces equal to 0. So I'm going to erase all this, draw a new free body diagram and a new triangle, and then I will be back once I have done that. Okay, so our forces are the same, except that our applied force is now an upward force 20 degrees above the horizontal instead of a downward force 20 degrees below the horizontal. It is also now a pulling force rather than a pushing force, which is part of the reason why it's up instead of down. So, we need to do the same thing again, split it into its components, which we're going to do with the triangle. This should be becoming old hat for you guys. So we have our triangle here, 20 degrees, FA. So FAY would be opposite FAX, good lord, would be adjacent. So FAX is equal to 260 times the cosine of 20, and FAY is 260 times the sine of 20, which gives us the same information that we had before. Our components are still the same. So our horizontal component is going to still be the 244, and our vertical component is going to still be the 88.9. The difference is that the vertical component is now positive instead of negative, which is an important distinction, to be fair. Now, from here, we need to write our sum of forces, so I'm going to redraw this diagram again up top. So we have our crate, we have a positive FAX, a negative FG, a negative FAY, a negative force of friction, and a positive normal force. And so from those, we can write our sum of forces. So the sum of forces in X would be the positive FAX minus the negative force of friction. But this time it is equal to the mass of the object, of the crate, times the acceleration that the crate is experiencing. And A is what we are trying to find. Okay, then we have our sum of forces in Y, which would be the normal force minus the weight of the crate minus the vertical component weight. I did this wrong. This is positive, so it is up. So plus the vertical component of the applied force. And now this crate is not traveling up at all. It's only traveling this way. So it's equal to 0 on the Y equation. So I'm going to separate this up a little bit. Now, do we know M? The answer is no. We don't know M, but we can find it very easily because we know that FG is equal to MG, and we know that FG is 1200. So then we know that M is equal to FG divided by G. So 1200 divided by 9.81 would give us our mass, which is going to be just a little bit more than 120. That's my phone, not my calculator. So that's going to give us a mass of 122 kilograms. So now, we don't know our force of friction, we don't know our normal force. We do know FAX, we know FG, and we know FAY. So we need to do some substitutions here. Now, we know that the force of friction is equal to the normal force times the coefficient of friction, which is also known. And we can determine with this that the normal force should be equal to FAY minus FG. So then we can plug this in up here for the normal force component of this. So, because the force of friction is Fn times mu. So we can plug this in for here, this in here, and that will give us one equation. So I'm probably going to erase this here in a second. In fact, I'm going to erase it right now because I'm going to use that space to do this algebra. I am missing an eraser. And I'm going to add that over here. So M, we determined, is 122 kilograms. All right, so I need to move. All right, so we're going to start here with FAX. So F FAX minus the force of friction, which is equal to the normal force, which is equal to FAY minus FF times mu equals M times A. That's supposed to be a G. FG. I just realized my head was in the way for that. So, FAX, I'm writing this equation and plugging stuff in. So FAX minus FF. FF is the normal force times mu. Normal force is equal to FAY minus FG, and mu is mu, and that's equal to the mass times the acceleration. We know this, we know this, we know this, and we got this in part 1, and we calculated this just a second ago. So the only thing we don't know is A. So we just solve this for A. So FAX minus FAY minus FG times mu all over the mass gives us our A. I'm not going to go ahead and calculate that for you since you have the actual number, but that is it for 14. You just have to plug and chug from there. So, hope this helps. These are a couple more examples of your equilibrium problems. Most of the problems you're going to be working with, you're going to have to set up some kind of an equilibrium system for. So, hopefully this helped out, and I will see you guys at some point.